Shmuel Weinberger, the University of Chicago, who will tell us about simplicial complexity.
Okay. Thank you. It's a real pleasure being here. I mean, this is my first time, and so I'm really glad to meet a whole bunch of people who I haven't met before. And, I congratulate the organizers for having brought interesting people for me to listen to. They're really good. Okay, I want to talk about two problems that at first I didn't realize that they were really different problems. One problem is this: you look at manifolds. Okay, so the whole talk will be about manifolds, by the way. And let's assume that their curvature is, their sectional curvatures are everywhere between -1 and 1, all sectional curvatures, and their injectivity radius is at least 1. Okay, so in other words, they're locally boring. Okay, right? I mean, I haven't, imposed a condition on the sign of the curvature, right? All that I've done is I've said that locally there's a compact space of structures, which means that I've sort of settled down on the local structure. And then I want to think about the complexity of M. Of M should be just the volume of M. Okay? And this is, and the key point about this notion is that with this you have finiteness theorems. Okay, these were first, this theorem, the fact that the class of diffeomorphism, the number of diffeomorphism classes of manifolds, I guess I should put in a dimension, because otherwise there are infinitely many with a given complexity. But for a fixed dimension, the fact that this is a finite set, that was in Cheeger's thesis. In Cheeger's thesis, he actually, instead of this, he put a lower bound on volume and then had the problem about getting an injectivity radius conclusion out of that. So, and that was in fact, more delicate and more interesting, etc. But I'm just going to assume this. And one could go, okay, and then the key point is that under this situation, there are finiteness theorems for the number of manifolds, right? So it becomes, so it makes you feel like talking about volume in this setting is, sort of a cool thing, okay? And for example, in dimension 2, okay, if you're going to be connected, then this will be basically just the Euler characteristic, and the number grows linearly with volume, okay? Unless you're allowing disconnected, and then it's exponential in square root of volume, okay? And in higher dimensions, you're exponential in about v log v, okay? And this is a theorem of Berger, Moses, Lubatsky, Galander, and I don't remember anyone else. So, okay, it's a paper called Counting Hyperbolic Manifolds, and the point is that even among hyperbolic manifolds, you have this many, and then so when I say x, I mean there's an upper bound that has some base of an exponent, and there's a lower bound, and the twain do not meet. I'm doing qualitative counting. Okay? I don't want to do actual counting. Okay, so this is one notion of complexity. Okay, and then there's a purely PL notion of complexity. Okay, which is how many simplices are there in a triangulation of my manifold M. Okay? And again, this same count is correct. Okay? And in fact, these two notions are very, very similar. If I start off with a manifold like this, then I could go ahead and triangulate. The fact that smooth manifolds are triangulable, that's actually a theorem. I mean, it was proven by, I think, by Cairns and Whitehead. And, and you could follow the proof. I mean, around, you look at the coordinate charts and you triangulate the coordinate charts and you move them a little bit to be transverse to each other. So you could really go ahead and turn one of these things into one of these, with a proportionate number of simplices. Okay? And in the reverse direction, there's, I think, a proof in a preprint of Fedya Manin and myself, but Januszkiewicz told me a few weeks ago that Calabi proved such a theorem, at some Arbeitstagung. Okay, so I don't know that it's in the literature anywhere, and I'm not sure that to be honest, I'm not sure I know how to prove it in dimension 4. But the theorem is that if you have a smoothable manifold and it has a triangulation of this sort, then you can actually put metrics on. So that these notions are extremely similar, except that there was one lie. Okay? And here's the importance of the lie. Okay? So smooth gives rise to PL, okay, with a proportionate number of simplices, PL plus a local boundedness of the geometry, okay? So of course if I have at most V simplices, my vertex has at most V neighbors, okay? But V is unbounded, okay, right? I mean, that's a bound, right? So, I mean, there's the following logical problem, right? If I start off with, right, in dimension 6, if I have a 6-dimensional polyhedron, the link of a vertex is going to be a 5-dimensional homotopy sphere. But suppose that some jerk goes ahead and hands me something where it's non-simply connected and I don't know it. Okay? So he told me it was a manifold and not. But then he says, go ahead and do Calabi theorem and give me a smooth structure. Obviously, I'm going to have to fail. Okay, so the smooth structure I build is going to have to measure the complexity of the, of the triviality problem for fundamental groups. Okay, so if you want to go back, you have to multiply by some constant that depends on the local geometry. Okay. So these are closely related notions, okay? But the PL one has, more room for local complications, okay? All right, so those are the problems that I want to discuss, and the philosophy is one that Gromov infected me with during a talk in the 1990s at Princeton. He gave a talk that was called long-range geometry. And it turns out he meant large scale. But anyway, he began talking about how topologists prove all these theorems and that we don't understand what any of them mean. And he gave, various examples so for example, René Thom worked out cobordism, so I have a manifold and I could figure out whether or not it's the boundary of a manifold 1 dimension higher. So suppose that I go ahead and calculate the invariance, and it is a boundary. What can I say about the thing that it's a boundary of? Okay, right? So that's sort of that it turns out that all of these theorems are just sort of like oracles, that we don't really understand anything after the fact. And then, that has been bugging me for more decades than some of you have been around. Okay, so that's going to be really the theme I want to talk. I'm ultimately going to be talking about manifolds homotopy equivalent to a given one, where there is some elaborate theory for how to construct such, about classifying manifolds. Okay, and what I really want to know is, can I understand the subject that I worked on for decades? Okay. But anyway, let me just have one concrete theorem before I tell you before I build up to it. So this theorem is not the main theorem of the talk, but it will contain all of the main ideas. Okay, and this is joined with Wen-Ho Lim and myself, and it actually even already appeared in the Krell Journal. And it says the following, that the number of simplices that are necessary to triangulate the lens space Ln 2D minus 1, which is just the unit sphere in CD, and where I identify u with e to the 2 pi I over n times u, okay? So this is a concrete manifold, okay? And okay, so the number of simplices for a fixed d, okay, is around some constant, depending on d, let me emphasize that, n to the d minus 1. Okay, that's the theorem. Okay, so I'm not saying anything about what happens as d increases. Okay, so like Karim Adi Presido loves these kind of questions, and he in fact gave examples of triangulations of RPN with a co-author. I apologize. I'm not well enough prepared to know about that orthogonal direction. You know, so that's one direction, and then, but in this direction, if you fix the dimension and you ask what happens as n increases, this is the rate of growth. Okay, except that this n should be capital N to keep the notation consistent. Okay, so let's see. So for d equals 1, right, so then we're the one-dimensional n space. So you're taking the circle and you mod out by z mod n, you just get a smaller circle, but then we said the injectivity radius, right, so the volume isn't divided by n, right? So this just says that it's around a constant, which is in fact exactly a constant. Okay, that one scores. Okay, in dimension 3, this is a theorem of Chun Cha that appeared in Communications of Pure and Applied Math sometime in the 2010s. I mean, I don't remember exactly, you know, about a decade ago, give or take. And in fact, you know, one kind of thing that people think about, oh, I can get a lower bound, right? I mean, if we're trying to understand what's the amount of complexity that something has, right? I mean, certainly in this audience, I expect people to say, oh, we're going to use simplicial norm. Okay, well, simplicial norm is fine and highly non-trivial, and it gives very interesting invariance, okay, and interesting lower bounds. I mean, that's indeed the case, but it's obviously not the whole story. But if I tell you that you have 500 simplices, there are only going to be finitely many ways that you could put it together, okay? And on the other hand, we know that, you know, in dimension 3, simplicial norm, you know, has limit points that come from, you know, taking, from cusp closing, right? And so so you could, so one of the things that Shah also studied, and it turns out to be very, very related to the theorem about lens spaces, is that, you know, as you close a cusp, even though it's not contributing to the simplicial norm at all, right? I mean, each of those, you know, it's sort of a linear growth in terms of, you know, which curve you fill in, how that gives rise to invariance about this. Okay, so a lot of what we, you know, our theorem has a lot of what we did is based on giving a more geometric approach. Hopefully some of the ideas behind it, I'll be able to do some more justice to the history. Okay, but anyway, so this is what I'd like to do. So in higher dimensions, this kind of estimate you could get very easily. You know, you start off with, you know, like a 3n-gon or something, and then you join it with itself d times, and then, you know, that will be preserved. Okay, it's not quite a triangulation, you subdivide, okay. Okay, and then you mod out by the zn action. So that suggests this to the d minus, and to the d minus 1. Okay, in this case, okay. Okay. Yeah, I just gave you the proof of the lower bound. That, you know, that's, you know, that it's easy to triangulate it with that many simplices. Okay. Okay. Right. I mean, you know, the very naive thing about taking this sphere, right? You know, I mean, the first thing that I thought of, you know, was the stupid thing, which was, you know, you take the sphere and then you rescale it so that the injectivity radius becomes 1, and when you do the rescaling, then you get the wrong rate. Okay, right? So I mean, because you've done too many directions. unnecessary dimensions. Okay. So here's the question that I really want to address somewhere along the lines, or talk about, which is how many of the manifolds with complexity at most v are homotopy equivalent to some given m. Okay? Because this is the subject of surgery theory. What are the manifolds homotopy equivalent to a given guy? Okay? So let me first tell you the miracle of surgery. Okay? So the miracle is that the set of m prime with a homotopy equivalence to m. Okay, this is a set, and modulo homeomorphism. Okay, so the homeomorphism, so if I have an m double prime and an f prime, if there's a homeomorphism that makes this diagram commute, then they describe the same element. But it could be that m and m prime are abstractly the same, but f and f prime don't differ by a homeomorphism, right? Like in Mike's talk, right? Then you view them as different. So the miracle is that in the topological category, in top and dimension bigger than 4, this is an abelian group. Okay, so this is something that's really miraculous. You can't imagine how in the world are you going to go ahead and take the union of two such things and produce something. And in some sense, all the people who do the Borel conjecture, right, they try to show that manifolds are homeomorphic, which is something that you could care about, is what they really do is study this group and show it's equal to 0, which sounds to me like something you might not care about. Right? I mean, this kind of thing, it's also, up in the air. Okay, so part of the mystery is like, how in the world can you be, is there any kind of geometric understanding behind this structure? Okay, so let me just talk about an example which, had I known before Gwen Ho and I started our work, we would not have been so optimistic about proving the results we did. So things are more, so like for the sphere you get 0 because the Poincare conjecture is true. Okay, right, we're working topologically here. PL, there's also a group structure, and it differs from the topological one only by finite order stuff. So we're not going to worry about it. And in the smooth case, it turns out that there is no group structure at all. Okay, which surprisingly, took decades to observe. Anyway, so this is this is what the abelian group happens to be. Okay. And for those who know about characteristic classes, it's not so hard. I look at a manifold homotopy equivalent to S4 cross S4. It has a first Pontryagin class. And the first Pontryagin class lives in the fourth cohomology, and the fourth cohomology is Z cross Z. Okay? So what you should imagine, so now the number of manifolds in here with V simplices turns out to be around V squared. Okay, so this is surely what one would expect, right? If you believe that there's some hidden geometry behind the surgery theory. Okay, right? I mean, if something or other turns out to be an abelian group, right? Surely, if you put in the complexity notion, the complexity should be related to the radius. And, this sounds like the rate of growth. Okay? However, in the smooth version, with volume less than V, this is around V log V. Okay? Which, one knew as an abstract statement that the smooth structures are a set and that there isn't a way to make an addition that's at least compatible with the topological one, etc. But this makes it very, very clear, that at the level of geometry, we're not going to be able to, that there are difficulties at the level of geometry. Okay? So in fact, the main theorem that, that Gwen Ho and I prove, if you were doing the smooth version, it's actually an inequality due to Cheeger and Gromov. But the nuance is that we do it differently than they do it. They do it analytically and work smoothly, and we were able to work PL directly geometrically, and that's actually why the talk fits into the conference, okay? Because the way we do the geometry will involve hyperbolization, so that we really, our proof for the number of simplices you need on this beautifully positively curved manifold goes via negatively curved geometry. Okay, so that was why I picked this topic to talk about. Okay, so anyway, so let me tell you what happens for RP 4K minus 1. So this thing here is, okay, they didn't know it was a group back in the olden days, okay, but the result was, it was Z plus finite, okay, and I'm not, people figured out what the finite thing is. I'm just not going to bother you. I mean, you don't care. You're not going to remember it after the talk, right? So it's about a Z. So this was discovered by Browder and Livesey in the 1960s. Okay, and let me explain to you what this invariant is, okay, because it's not Pontryagin classes. Okay, so here's how it goes. I take my manifold and I look at its twofold cover. Okay, and inside of that manifold, I could find inside of here some n of codimension 2 that has a free involution on it. Okay, and the way I find it is just that I had the homotopy equivalence to RPN. I take the transverse inverse image of RPN minus 1. Okay, so then when you lift it up here, you could arrange for this thing to be connected. Okay, and you have this kind of action on it. Okay, so far so good. Okay, and the thing is that this involution is orientation reversing. Okay, that's the nature of this involution. Okay, and what you now do is you say Browder-Livesey of M is the signature of the quadratic form on H n minus 1 over 2. Okay. Okay, of the quadratic form U cup TV. Okay, okay, normally when we talk about a manifold, we say the signature of the manifold is just the signature of its middle dimensional cohomology. Okay, and that's an oriented homotopy invariant, and you get an integer, blah, blah, blah. Okay, over here, you use the orientation reversingness to give you a switch. So instead of in dimensions 4K getting a signature, when this codimension 1 thing is 4K plus 2, you get a signature. Right, the skew symmetry of the inner product together with the orientation reversingness of T gives you a positive definite, not a positive definite, a genuinely symmetric inner product pairing. Okay, so this invariant in the integers turns out to always be a multiple of 8, but we don't care. You know, for our crude purposes, that's what this Z is. Okay, and now if you think about it, this being cohomological, you can see that the number of simplices in the original manifold M, you know, can be used to give a bound on this, right? I mean, you have a map, and then you have to make it transverse, so whatever's happening, the geometry is all bounded by the number of simplices that are going on. So whatever this kind of inner product is, so for this, right, so this Z, which is the main part of the story, in dimension 4K plus 3, that really does grow at most linearly in the number of simplices. So then you need to have a construction of guys with a linear number, and indeed that's the right estimate. Okay, so I guess I could call that a theorem, right? The Browder-Livesey invariant is around proportional to V, if you know what I mean. Okay, and you know, so that we understand for this case of RP 4K plus 3. Okay. And so this is, so by the way, so this is what surgery theory does. So, people tend to remember the extreme cases like the Borel conjecture where it predicts 0 as the answer. That's easy to remember, right? But for, say, simply connected manifolds, it boils down to being the cohomology. And when you're not simply connected, it's frequently complicated about what it is that these predictions are. Okay? Okay. So next I have, it turns out that if I look at a lens space, so I'm going to pick P and odd prime just because I don't want to remember formulae. Okay? So then this thing here is Z to the P minus 2. Okay? That's what the answer is. Okay? In fact, there isn't even a finite part. It's on this is sort of the right answer. And it breaks up into 2 pieces. There's a Z to the P minus 1 over 2. And there's another piece that's a Z to the P minus 3 over 2. Okay? Okay? This isomorphism is well known and, not due to me. Okay? This part here this is the invariant that Reidemeister and Durham used to distinguish linear lens spaces. Okay, you could do the same construction I did, but instead of using the same root of unity on every coordinate, you could use different roots of unity. And the theorem is that those manifolds are diffeomorphic only when they're obviously diffeomorphic. Namely, that conjugating representations to one another. So that old theorem is based on an invariant over here. Okay? And this part here also, dies after you cross with a circle. Okay? So, if instead of asking if the lens spaces are diffeomorphic, you say I'm interested in what happens after I cross with a circle, then you lose this half. Okay? The slightly smaller half. Okay? And this part here, this is a generalization of the Browder-Lipsey invariant. Okay, and it was, I think it's either due to Atiyah Singer, or Atiyah Bhatt, or Atiyah Patodi Singer. But definitely Atiyah is part of it. They introduced this in studying spectral asymmetry, or the work with Bhatt had to do with Lefschetz numbers for invariant differential operators on manifolds. Anyway, whoever we blame, the fact that this is the same thing as Browder-Lipsey for Z mod 2, that's a theorem of Hertzebruch. Okay? And what I don't want to explain, but is critical for the talk, okay, is that this here has a generalization due to Cheeger and Gromov. Using L2 cohomology. Okay? So for people who know Atiyah Patodi Singer, there's some signature operator going on, and then there's the signature operator has a spectrum. Let's assume that it has no spectrum at 0. You form an eta function, and then they say that function is it's defined for the real part large. You do it, and then they show that there's a meromorphic continuation. They take a value at 0, and then they show that some combination of this may be associated to the regular representation minus the trivial representation, or maybe associated to various representations, that quantity is independent of the metric on the manifold. Okay? And what Cheeger and Gromov did was they did the same thing, except they went to the universal cover and used L2 as being the way you renormalize. Okay? So there is some invariant, which I will call Cheeger-Gromov of M, which is a real number. Okay? And I'll give a drop more details than I did just now, okay? And, okay. And let's see, let me just, okay. So with the things I've said so far, I can now state a few theorems, okay? And all of the theorems that I'm going to state are joint with Lim, okay? Who's a postdoc now in Paris with Adi Presido, by the way, just for people who want to locate him. So the first one is that the number of H cobordism classes of manifolds homotopy equivalent to a lens space is V to the P minus 1 over 2, okay? So this is a weaker equivalence relation. This is equivalent to the after crossing with a circle, okay? And the number of manifolds in the smooth case is V to the P minus 2, like it should be, okay? So that's the theorem with respect to lens spaces. Okay. What it is, there's a problem here, right? Basically, the point is, in terms of this dichotomy, is that we figured out how to handle the Cheeger-Gromov invariant, right? The analog of these Browner-Lipsey invariants, but we didn't figure out how to handle these torsions. Okay, and the analog of what we're missing for a classical torsion. So let me just tell. I mean, maybe 3/4 of you know this, but the quarter of you who don't will benefit from this. There's a wonderful thing called Gabber's lemma, which says that if you look at a simplicial complex that has at most n simplices, then the order of the torsion in its integral homology is at most exponential in n. Okay, right? So that's a statement about homology. And it's sort of, if you like, an example of this general philosophy, right? How does complexity of one sort get reflected in complexity of invariance? And there are sort of these great conjectures, for example, that for three-dimensional hyperbolic manifolds, that the growth of the torsion is exactly as predicted by that exponential when you go ahead and relate it to this kind of invariant. When you relate it to an L2 torsion, that actually makes the prediction. Okay, so somehow what's missing is some kind of version of Gabber's lemma in algebraic K theory, as opposed to just talking about integral homology. Okay. Okay, and the other part of the theorem is that the Cheeger-Gromov invariant of M is less than or equal to some constant, depending on dimension, times the number of simplices in M. Okay, and this I want, okay? And this is what Cha proved in dimension 3. And Cheeger and Gromov did this for, in all dimensions using volume. Okay? Okay. So let's see. This obviously proves half of the theorem, right? Because it tells you that you look at this you have this free abelian group, and this tells you about the radius. What's the radius of the sphere? So then you have to complement it with a construction, and I'm not going to tell you about the construction. Okay, so so this is about half of that. Completely opposite methods to each other. The surgeons would have no trouble doing the half that I'm ignoring, and and this is the interesting part. And I have to. So what Cheeger and Gromov did was analysis, right? You have to do spectral theory on the universal cover, and you have to get bounds on eta functions. They immediately modify the metric to improve its differentiability, and so on and so forth. So at least it seemed to me that I didn't know, that I couldn't figure out how to get around the bounds on geometry. Okay? So, you know, I mean, it's possible that Misha will have another proof when I talk to him next week, explaining this inequality in all dimensions. Okay? And then, oh, and the other thing is, oh, and this implies this, because what, as you might guess, when you compute the invariant, it's exactly the other side. Okay? So I'm not going to tell you how you compute the invariant. It turned out that the computation of the invariant, even though it wasn't defined at the time, was done by Atiyah and Bat in the 1960s. Okay? Let me just comment, the paper of Atiyah and Bat was at the time a proof using this invariant that lens spaces that are different from each other are not diffeomorphic. You know, the fact that if they're not linearly the same, they're not diffeomorphic. It turns out that either of the invariants is strong enough for that. One of them, you know, is weaker, that it's not invariant under H cobordism, so it goes away after you cross with a circle. Okay, but the other invariant. Okay, so let me talk about this other invariant. Oh, let's see. Yeah. There's one thing I said that I think might be confusing people who are too polite to interrupt. Okay, right? This invariant is just a real valued invariant, and I'm using it to get estimates on the size of a ball in a higher dimensional vector space. So that seems like a trick. And remember, I'm only bounding using L infinity norm, so I can't even say, oh, I'll show that various numbers are rationally independent. Yeah, no, the point is that this Shiger-Gromov, the proof that we gave enables you to do this together with some twists, using the representation theory of the fundamental group. Okay, I mean, it's sort of not enough. To just pull it out of the theorem directly. There's sort of some really nice pictures that go into this, which Gwen Ho was able to produce. And I won't be able to do it. So let me explain the Shiger-Gromov invariant. There were two papers that, well, Chatterjee and Mislin never talked about the Shiger-Gromov invariant, but Chang and I did. Okay, these were somewhere in the 2010s. Chatterjee, I'll get to what these papers do. Okay, but let me explain what so L2 cohomology. I don't know what to say about L2 cohomology other than to say, I'm going to start with a map with M. I then go to the universal cover, which is acted on by pi 1 of M. Okay, of course I could take any regular cover and get some kind of L2 cohomology associated to that. Okay, then I look at the cohomology based on forms, let's say, use real coefficients, based on forms with L2 decay. Okay, so I could never take, say, a cohomology class downstairs and pull it up. Okay, that's forbidden. Okay, it still satisfies Poincare duality. Okay, it's still if I have a homotopy equivalence downstairs, it lifts to the right kind of map, so that there are induced maps in L2 cohomology. It's a thing, and then the wonderful thing is that the dimension of HI L2, it's a non-negative real number. Okay, it's equal to, so here by definition I'm going to say that this is the kernel of the Laplacian on star forms. Okay, otherwise there's an issue that the image of D, it might not be closed. So there are sort of two slightly different L2, well, two L2 cohomologies that have different feelings to them, okay? And when you're an expander, then you have some region around zero that's free, and then the notions coincide, okay? But just to relate it to other things in the talk, in the conference. Okay, so one forms these things, and these are called the L2 Betty numbers of M. So there's a theorem of Atiyah that the L2 Euler characteristic of M is equal to the Euler characteristic of M, right? So this is the alternating sum of the L2 Betty numbers, and this is the alternating sum of the Betty numbers, okay? So that's one part of his theorem. Both of these things that I'm about to say are corollaries of the main theorem of Atiyah's paper. The other one is that I could now form an L2 signature of M4K, and the theorem is that that's the same thing as the signature of M. Okay, so I talked about the signature, right? You look at the middle dimensional cohomology, it has a symmetric bilinear form. You diagonalize it, you look at the dimension of the positive part minus the dimension of the negative part. That's the signature of M. In the universal cover, I use L2 theory to form the same quantity. I get a difference of real numbers, and this difference is the same as those. Okay, so that was the theorem of Atiyah, and which Atiyah proved by proving the index theorem for L2 for the L2 situation, and observing that the Atiyah index theorem is the same. It's computed in exactly the same way as the Atiyah-Singer theorem, and that therefore these quantities were the same. Okay. This part here is decidedly less deep than this one. That these two things are the same. This one here, when you take Betty numbers and you define Euler characteristic using different fields, you also get the same number, and there's a purely algebraic proof. Okay? And however, and so then if you enlarge your point of view enough, you know, to include a little bit of algebra, then you could also prove this by the same method. It's just really a theorem about chain complexes. Okay? This is not true. It's not a theorem about chain complexes, right? This says that we form that signature notion, right? Right, and it's saying, and if I say take a space that satisfies Poincare duality, and I look at a threefold cover, which also satisfies Poincare duality, it isn't the case that the signature is automatically multiplicative by 3. Okay, so this is saying that it's true for manifolds, and that was a consequence of the Hertzebruch signature theorem. Okay, okay, it's because there's a local formula for signatures, right? That is sort of the source of this. Okay, so this is sort of algebraic, you know, in origin, and this is sort of more geometric or analytic, depending on your predilections. Okay, so the paper of Chatterjee and Mislin is going to, which I'm about to explain, explains how you prove a Atiyah theorem without analysis. Okay, okay, so okay. 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 So now, you know what okay, so definition / proof of Atiyah's theorem / who knows what else goes like this. Okay, I'm gonna do everything simultaneously. Okay, is that as well as, so this is the definition of the Cheeger-Gromov invariant simultaneously with the proof of Atiyah's theorem. Okay, so it goes like this. It says, so if I'm going to, I take M4K, maybe I'll use a different letter. I'm going to take a 4K minus 1 dimensional manifold. So in fact, I'm going to say it like this. N4K, I'm going to say it positively. N4K minus 1 always bounds a manifold W, where the other boundary is N4K minus 1. Okay, so far everyone knows the proof, right? I just take N cross I. Okay, so this doesn't buy you very much. Okay? 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 Such that, so that the maps from pi 1 of the two copies of N, which I'll call N plus or minus, into pi 1 of W inject, okay? That part still is holding, but here's going to be the interesting part. Here I'm going to go to pi 1 of W modulo the normal closure of pi 1 of N. Okay? Okay, so now that's something. So then this bottom one, pi 1 of N minus, okay, right? This bottom one is no longer injecting in this group, but this thing here is injective on pi 1. Okay? So this is going to be a statement. Okay? And the Cheeger-Gromov invariant of N is, what do I want to say? It's the L2 signature of W minus the ordinary signature of W. Right? W is a manifold with boundary, so you could go of dimension 4K, right? So you could still look at the product pairing. It's now singular, right? It has some null space that comes from the cohomology of the boundaries. So ignore the null space, mod out by it, so that you then have a union modular form, and you diagonalize that, and you can form the signatures. Okay? Now, for Euler characteristic, doing anything pathetic like that isn't going to change anything because it's a theorem about complexes, right? But for manifolds with boundary, there's again no reason why the fact that you could define a signature for manifolds with boundary, why it's going to become multiplicative when we pass to finite covers, or asymptotically when we go to the infinite cover. And so this is what the Cheeger-Gromov invariant turns out to be. Okay, so this is a real number. Okay, and it's the this is the Cheeger-Gromov invariant. Okay. And this includes a Tia theorem when we apply it to the empty set, right? Because then I'm just having the manifold W, and I'm saying I'm formed that difference, and that's supposed to be 0, right? The statement that this is an invariant, right? Calling this a definition is a theorem, okay? And okay, this isn't exactly, so now let me, okay, so let me sort of, I'm going to first prove something that's somewhat weaker. That was sort of the first approach, okay? The first approach actually went like this. So the original approach went, like, instead of here you would have N, and down here you would put a W. You try to find a closed thing that N bounds. And here I want to put a W4K. Okay? The problem is that this W doesn't necessarily exist. That's Rene Thom's cobordism theory. Okay? Not every manifold is the boundary of something. Okay, so that's the problem. But if I take a number of disjoint union, number of copies, right? So Rene Thom showed that the odd cobordism groups are torsion. So therefore you could multiply by something. So you would take R copies of N, and then you would divide by R. Oh, damn. Okay, that's my warning that my time is up. Okay, I only have time for questions. Okay. Anyway, so well, that's bad news. Okay. So I'm going to now ask myself a question. So what do you do next? Okay, good. Okay. But what you really need to do L2 theory is you need to have injections on fundamental groups. Okay, because there's this property that when I take a group and I include it into a larger group, and I take the induced gadget, the induced regular cover associated to that, I get many copies of M, but the L2 Betty numbers are the same. Okay, so using things that are inject, gives you power, and that's sort of what happens here. Okay, if I look at the regular cover associated to this, I will have a lot of copies of the universal cover of M, which are the things that Shiger and Gromov wanted us to have. And then down at the bottom, I have a whole bunch of copies of the original N, with nothing going on for them. So for this, the L2 signature is just going to be the ordinary signature. And for this one, you've really studied the object that you want. So the key point, which is done by a version of hyperbolization that appeared in an appendix that Mike Davis and Januszkiewicz and I wrote to a paper of Mike and Januszkiewicz that appeared 10, 15 years after the original paper. But basically, that's what our construction is. That if you start off with a manifold, you triangulate it, and for each you inductively go over the simplices, and you build some suitable object like this. So the size of W, the number of things in the construction, is bounded by the number of simplices that are occurring. Okay? And once you have that, then this invariant is good enough. Okay, so I think that that's all I have time to explain, so I'm done.
Questions?
Maybe I misunderstood something, but so somehow the goal is you have to, given an n, you have to find a w with the property that n has got two n's and
yes.
n injects after you kill this n.
Right. Yeah. Yeah. So basically, so what you do is you do a hyperbolization to the cone on n, and you delete the cone point, and that ends up having the right properties.
I see.
Okay. Yeah. So in the thing that, so in the paper of Davis, Januszkiewicz, and mine, we were trying to prove an assertion of Gromov. Gromov had said that, firstly, every cobordism class includes an aspherical manifold, and that was what Davis and Januszkiewicz did that in their first paper. And he also claimed that if you have two cobordant aspherical manifolds, they were cobordant through an aspherical manifold. Okay? And that was open for a while. And what we realized was that there was if we knew that the cobordism between the manifolds had pi1 injecting, then you would be able to achieve that. But so then you need to do the opposite of surgery, right? In surgery, you kill fundamental group. You want to do the opposite of surgery. You want to take something where the fundamental group died and replace it by a cobordant object, by some other object which has fundamental group. So we did that at the time, like Chatterjee and Mislin, using an embedding of the group into an acyclic group. So such things were constructed by Baumschlag, Dyer, Miller. It was real geometric group theory. It was real homological group theory. I don't know that I would call it geometric group theory. That was that approach, and Jean-Claude Haussmann also had used acyclic, had pioneered the use of acyclic groups. So, that was sort of like this fun trick of using acyclic groups as a way of replacing analysis by group theory. And what Cha did was he took this kind of construction and he did it purely homologically. He removed all the manifolds, etc. And managed to get a chain complex thing explicitly in dimension 3 with a lot of pain. And what Lim's thesis was improving the constant in Cha's estimate. But I just couldn't understand it at all because I understood the analytic thing, and I couldn't see how algebra would do it, and I never understood the algebra, but instead this was the geometric reinterpretation which works in all dimensions. So that's sort of how this goes. And then you could, of course, when you're taking cones, you could reinterpret it in terms of prisms.
You say a little bit about how the proof, so you say you're taking the cone on the manifold.
Right.
You're tweezing the cone on your hyperbola, and then say a little bit about why the pipeline gets where the power injectivity statement comes from?
Oh, well, because, it comes out of some non-positive curvature of the hyperbolization.
So you're sort of showing it's totally geodesic or something?
Yeah.
Okay,
yeah. Yeah, so that's where the pi1 injectivity comes from. Yeah, so first we used acyclic groups, and then Tadeusz realized that, oh, we could just go back and use hyperbolization right away on polyhedra and get the pi1 injectivity. So actually using the acyclic groups, we wouldn't know how to prove this kind of, we'd have this, but it would be all the usual lack of understanding of topological oracles. Okay, the best information we know about cobordisms that exist for algebraic topology reasons is it grows like a power of the volume of M to the 1 plus epsilon, where epsilon is anything greater than 0, but it doesn't quite get you linearity. So I have no idea how to prove a result like this, you know, not explicitly. But explicitly, you know, you just take your favorite hyperbolization construction and it will work.
Any other questions? And coming, thanks, Shmuel, and thank you.